Yeah. Christian misses you. All right. So here's the sample problem number 1. A solution is prepared by adding 750 mils of 4 times 10 to the negative 3rd molar cerium nitrate to 300 mils of 2 times 10 to the negative 2 molar potassium iodide. Will cerium iodide precipitate from this solution? Yeah, so when you get it, there's a whole lot of stuff going on. First thing is calculate the ion concentrations of both ions. Now, in reality, aren't there 4 ions? Yeah. Cerium, nitrate, potassium iodate. But 2 of those we don't care about because they're not going to make a precipitate. And they are nitrate, because all nitrates are soluble, and potassium, because all group 1s are soluble. If you ever need to know the 2 ions that you're concerned with, look at who they gave you the KSP for. They gave you the KSP for cerium iodate. So those are the 2 ions, the cerium and the iodate, that we're concerned with. Those are the 2 ions we care about, okay? Ce plus 3 and IO3 minus. Now, go.
Didn't we do problems like this before? With the soluble and soluble problems.
Right, we've done, correct. But now we're going to see if an insoluble product, if there's enough ions of the Ce and the IO3 to actually generate the precipitate. So we know that's insoluble, but whether or not we're going to see it is the question, okay? Yeah, so we've done double replacement reactions before just using solubility rules, but this takes it one step further, okay? The next question is, well, don't we already have the concentrations? Well, kind of. We have the concentrations of them when they're in separate containers. We're going to mix them, right? So when we say calculate the initial concentrations of both ions, it's when we mix them together, not when they're separate. So to do this, I'm going to call this step 1. The easiest way to do it is to do an M1V1 equals M2 V2, where your 1s are when it's separate by itself, and then the 2s are when mixed. Okay? And we'll need to do this for both ions. So the first ion is Ce, right? We'll do that one first. Initially, we have 0.004, right? 4 times 10 to the negative 3rd is 0.004. And we have 750 mils of it. It's okay that your volume's in milliliters as long as it's in milliliters on both sides. When we mix them together, we want to know what's the molarity going to be when the total volume is, what is it, 1050? Right? So this V2 is your total volume once you mix them together. So 300 plus 750, which gives you the 1050. And if we solve for our x, we should get, I think I got, 0.00286 molar. And that's your concentration of cerium ions when mixed, okay? We're going to do the same thing for the other ion we care about, which is the iodate ion. So we'll do an M1V1 equals M2V2 for iodate. M1 for iodate is what? 0.02. Okay? I want to caution you here. If iodate had like 2, like a subscript of 2, or cerium had a subscript of 3 instead of the nitrate having a subscript, remember you'd have to multiply that by the concentration before you plug it in. We're not concerned with the concentration of the whole thing. We're concerned with the concentration of just that ion. So what I mean, and don't write this, but if there was a 2 here, then I would have to double that concentration before I plugged it in.
So but we don't have to for that, even though there's a subscript of 3 for that.
But that's not, okay, yeah, that's a good question. You don't have to over here because that's what we're going to make. That's not what we have right now. Okay, so you only look at the solutions that you have right now. Since if there's this molarity and there's only one iodate in that, then iodate has that molarity.
Okay, so that would just be for the M1 V1 if you were to do that.
Correct. Okay? So M1 is 0.02, V1 is 300. What is the molarity going to be when we mix them together? And there's a total volume of 1050. So my X, which is my concentration of iodate, is going to be, it looks like I have 0.00571. Okay? So that, God bless you, that's step one. We have calculated our initial concentrations when we mix them together by doing an M1 V1 equals M2 V2 for each ion. Now we will calculate Q. Okay. Q is always for the dissociation reaction. Okay? So before I calculate Q, I want to write the reaction for the dissociation of what might form. It seems kind of backwards, but that's what KSP is for. So we have to, and if we want to compare Q to KSP, it has to be for the same reaction, which is always the dissolution reaction. So this is our solid, and that will dissociate into Ce plus 3 and 3IO3 minus 1. So Q then will equal your concentration of cerium floating around in the container once you mix them, times your concentration of iodate floating around in the container cubed. Okay? So now we plug in the values that we just calculated. We use concentrations here. 0.00286 times 0.00571 cubed. And that will give us our Q. Which I don't have. You should get 5.3. 2 times 10 to the negative 10. Okay? Now, step 3 is to compare that to K to see if we're going to make a precipitate. So the K was given in the problem. The KSP is 1.9 times 10 to the negative 10th. Okay? Is Q greater than or less than KSP? Greater than. First look at the exponent. Since they're the same exponent, then you can look at the number that comes first. So this is greater than KSP, which means we have too many ions. So that dissolution reaction will shift left and a PPT will form. Because if this reaction shifts left, up here, right, you're going to generate more cerium iodate. Okay? Those are the basics. If you look at the next page, it gets a little more complicated. Hopefully we'll get through this page. My story took a little more time than I thought. Oh, I think it's encouraging. I know, we need a science fair. In addition, maybe I'll start back here. In addition to predicting whether or not a precipitate will form, we also want to calculate the equilibrium concentrations after the precipitate forms. So, not only are they going to ask you if a precipitate forms or not, but they're going to ask you what are the concentrations remaining in solution after equilibrium is established. So look at the example. calculate the equilibrium concentrations of Pb plus 2 and I minus in a solution formed by mixing 100 mils of 0.05 molar lead nitrate and 200 mils of 0.1 molar sodium iodide. First step, is a precipitate even going to form? Because the problem's going to be really easy if it doesn't. And sometimes it doesn't. I don't want you to think it's always going to form. So step 1, determine whether or not the precipitate forms when the solutions are mixed, which is what we just did. So we do an M1V1 equals M2V2, okay? We calculate Q, we compare it to K. We have to follow those 3 steps we just did, right? We need initial concentrations of the ions that are involved. Then we need to calculate Q. And then we need to compare it to K. And that's only in step 1 of this problem, which was the last 3 steps of the last problem. Okay, so go ahead and go to work, calculate, see if the precipitate's going to form. We'll come back in, say, 5 minutes. We'll resume this. So we calculated our initial concentrations. Check yourself with me. When we mix the solutions, for lead I had 0.0167. For iodide I had 0.0667. I calculated Q to be 7.42 times 10 to the negative 5th. I compared that to KSP, which is 1.4 times 10 to the negative 8th. Since Q is greater than K, the reaction shifts left, which means you'll make a precipitate. So because they asked us what the concentrations are in equilibrium after the precipitate forms, the next step is we need to form the precipitate. Okay? And it's only because they asked us what the concentrations are remaining in equilibrium after the precipitate forms. Now, if you notice, the KSPs for lead and iodide, or the KSP for lead iodide is really, really small, which really means that the formation of the precipitate is favored, right? That reaction, this one, Pb plus 2, just the reverse of our dissociation reaction. That's favored, okay? This is the reverse of the dissociation reaction. It's the precipitation reaction, right? And so the equilibrium expression for this would be K for the precipitation reaction is equal to 1 over KSP. Because remember from back in chapter 13, if you take the reverse reaction, you take 1 over the K, right? So we can get the K for this reaction by taking 1 over the precipitation, or the, the solubility dissociation reaction, and take 1 over the K. 1.4 times 10 to the negative 8 would give us the K for this reaction. 7 times 10 to the 7th. That's a big number. It's a really big K. In fact, it's so big that we're going to say that this reaction goes to completion. In reality, it does not, but we're going to say that it does. It will ease our calculations. So the equilibrium position of this reaction lies far to the right, and we will assume the reaction will go to completion. So the PB and the I2 are going to get together, the two I's, are going to get together until someone runs out, okay? So what that means, if it's going to go to completion, we have to do a reaction to completion to make a precipitate. And when we do reactions to completion, we use moles or millimoles. Okay? So what do we call them? A RICO box, right? Isn't that what we called them? So our reaction is our PV plus 2 plus 2I minus going to make PBI2 solid. Okay? And we're going to do our initial millimoles here. Now this initial millimoles is when they're mixed, right? So if we go back to our calculations on the previous page, we had 0.0167 molar of this, right? Times our volume, which was a total volume of 300 mils. So that'll give us our millimoles of the PB, which are what, 5.01? And for the I2, we had 0.0667 times 300, which would give us our millimoles of 20.01. And we didn't make any solid yet. So the change to get to equilibrium, or get to completion, is this limiting reagent problem. And unfortunately, they're not in a 1-to-1 ratio. Right? But they're pretty simple. If this goes down by 5.01, how much would this go down by? 10.02, right? And you have 20. So this is your limiting reagent. If it's not that simple, then yes, you'll have to do a limiting reagent problem to figure out who's going to run out first. So this goes down by 5.01. This goes down by 2 times 5.01. And this goes up by 5.01. So at the, why was it RICO?
Over.
When it's over, we have none of this left. We have 9.99 millimoles of this. And we have 5.01 millimoles of this. So I can get the concentration of iodine when this is over. Right? I won't get, the solid doesn't matter because it said concentration of all ions remaining in solution, right? I can get the concentration of iodine by just dividing this by my volume, 300 mils. And what we get is 0.033 molar. After the precipitate forms. But I can't say 0. You can't say there's no lead ions left. We don't say 0 because in reality there are some. So, you're not going to like this, just so you know. We have to now do a rice box. Remember usually, like, if we go to completion, then we got to do a rice box anyway, unless it's a buffer, and these are not a buffer. So now we have to go to a rice box because at equilibrium, the concentration of lead does not equal 0. The best way to think about it is that once you make the solid, a tiny little bit redissociates. I know. Okay? And so now, if you go to the next page, now we do our rice box. Now we do the equilibrium calculations. So I want to make it perfectly clear that when you react to completion, you do the opposite of dissociation. But now that we made the solid, now we're going to do the dissociation reaction. Where, okay, we made the lead iodide, and now a tiny little bit of it is going to redissociate. So it's like you assume it goes to completion, but it really doesn't, but this is the only way to do the calculation. So we've got some of this. Who really cares how much? We don't have any lead, right, because it was a limiting reagent and it ran out. And we have 0.033 molar of this left over from the precipitation reaction. This goes down by x, this goes up by x, this goes up by 2x. So at equilibrium, who cares about this? We have x and 0.033 plus 2x. So now, since this is the dissociation reaction, KSP, which is equal to 1.4 times 10 to the negative 8, equals our concentration of lead ions times our concentration of iodine ions squared. Now, small k, right? So we can assume x to be negligible here. So 1.4 times 10 to the negative 8th equals the concentration of lead, let me just go back up here so we can see them, is our x times the concentration of iodine squared. And our x turns out to be 1.3 times 10 to the negative 5th molar. So the answer to this question is that at equilibrium, our concentration of iodine is 0.033 minus 2 times 1.3 times 10 to the negative 5th, which is 0.033 in sig figs. It won't always be that way. Sometimes it may change the number slightly, so you want to plug it in anyway. And our concentration of lead isn't 0. It's just really close to 0. 1.3 times 10 to the negative 5th molar. So, when they ask you if a precipitate's going to form, that's really an easy question. But if they ask you to calculate the concentration of all ions remaining in solution, that adds about 10 minutes worth of work. Okay? Minimum. Minimum. We will finish. I was hoping to get done, but we didn't. We will do more practice with this tomorrow, no worries, and we will wrap this up for tomorrow. I have a couple AP problems I want you to try for tomorrow. I don't know where we are. Homework number what? 8, which is what? Does anybody know the problems in front of them?
89.
80 what?
89. 91. 96. 97. 99. 100.
Let's do this. I'll give you the 2 AP problems and then just do the first 2 questions from that homework. Okay? Yeah, don't get all excited because you know how the AP problems are. Yeah. So just the first 2 problems from homework number 8. Someone hit F10 on my computer to stop that from recording.